Hello, and welcome to the next installment of Fluid Statics. In this video, we're going to go through several examples to illustrate how to use the ideas so far. So example 1 is, we're going to ask, what is the absolute water pressure at a depth of 10 meters in the tank shown? Well, you can't see the tank yet, but let's go ahead and draw one. So, tanks have walls, bottoms, and they're filled with water. And this height, we're told, is 10 meters, and we're after the pressure down here. PB equals, we know up here that the pressure at the surface is 101.3 kilopascals, and we're going to use that absolute pressure and the hydrostatic equation to answer the question. So what's known? The liquid is water. Therefore, the density is 1,000 kilograms per meter cubed, and the specific weight is 9,800 newtons per meter cubed. And if we didn't trust ourselves on that, we could go out to one of our web tools, go to the toolkit, fluid mechanics tools, property of liquid water, probably 25 degrees C would be a good guess, and it says density here is 9781. Maybe we're at 20 degrees C. 9790, 9800 newtons per meter cubed is going to be adequate. So we'll return to our problem and continue. The depth is 10 meters given. The atmospheric pressure is 101.325 kilopascals absolute. I'm going to use 101 kilopascals because that should be close enough. That's at standard temperature and pressure. Governing equations, well, let's see what's unknown. Unknown is pressure at the bottom. Governing equations, well, it's dP dz equals minus rho g, or PB equals P0 plus rho g h, where h is positive downward from the surface. And so we'll use that approach. Solution. Well, let's apply this version of the equation. All we have to do literally is substitute numerical values. PB is equal to 101 times 10 to the third pascals plus 9,800 newtons per meter cubed times 10 meters, which equals 101 times 10 to the 3 pascals plus 98 times 10 to the 3 pascals, which equals 199 times 10 to the 3 pascals, which equals 199 kilopascals absolute. So almost 2 atmospheres. Okay, discussion. There's not much. Important points were to measure down from the surface and express in consistent units. That's why you notice I made the change from pascals to kilopascals here, so that a Newton per meter squared is a pascal. I don't have to deal with the kilos until the end. All right, that's a very simple problem. Let's continue. Next example, almost the same, although instead the tank is going to be filled with oil and water. So, what is absolute pressure at the bottom of oil water separator tank? Again, we need to draw a tank. So there's our tank. We'll have water, which is blue. Then we'll have oil, which is black. Hey, black and blue, the color of a hematoma. And we need to know our various dimensions. There are 2 meters of water from the bottom, and then a meter of oil floating on top of that. Okay, the specific gravity of oil in this instance is 0.8. The specific gravity of water by definition is 1.0. And we know that the pressure here is 100. I'm going to use 100 kilopascals. It's close to 1 atmosphere. Make the arithmetic easier. In your analysis, you might choose to choose 101. And we want to know what the pressure down here is. We'll call that P2. I'm going to introduce an intermediate pressure, P1. We're going to need to, if not directly calculate it, it's going to be incorporated into our algebra, so we might as well include it. So let's list our knowns. Water, specific gravity equals 1. Gamma is 9,800 newtons per meter cubed. Oil, specific gravity is 0.8. Gamma will have to compute, but it's equal to 0.8 times 9,800 newtons per meter cubed. The height or the depth of the oil is 1 meter. Depth of the water is 2 meters. And we've arbitrarily set our upper top pressure at 100 kilopascals absolute. Unknown. Well, there's a lot, but in this case, P1 equals P2 equals Governing equations. Well, we're going to have PB equals PA plus rho G delta H measured downward we're going to use Pascal's law. And we will first apply the equation in the oil to find P1, then apply equation in water to find P2. Well, let's do that. So P1 equals P0 plus rho oil G delta H. That equals 100 times 10 to the 3 newtons per meter squared. That's our kilopascals. Plus 9,800 newtons per meter cubed times 0.8 because of the specific weight of the oil times 1.0 meters high. This equals 100 times 10 to the 3 newtons per meter squared plus 7.84 times 10 to the 3 newtons per meter squared, which is 107.84 times 10 to the 3 newtons per meter squared, which is 107.84 kilopascals. Now we go for P2. P2 equals P1 plus rho water, G delta H, there should be an oil there, water. So 107.84 kilopascals plus 9,800 newtons per meter squared times 2 meters equals 107.84 times 10 to the 3 newtons per meter squared plus 19.6 times 10 to the 3 newtons per meter squared. That comes out to equal 127.44 times 10 to the 3 newtons per meter squared, which 127.44 kilopascals. So that's the absolute pressure. By way of discussion, we have two liquids. Start at top and work down. Find the pressure at each interface until you get to wherever we need to. The second, probably most important, was to use specific gravity to relate gamma oil to gamma water. And as you recall, the specific gravity is defined as gamma oil over gamma water. Actually, gamma of the unknown over gamma water. Remember to correct the gamma for the portion of the fluid examined, in this case the oil. And if we were interested in gauge pressure, well, the pressure in the gauge would simply be the absolute pressure minus the reference value. So let us suppose, for the sake of argument, that the reference value was, well, we wanted this in gauge pressure. In gauge pressure, the results would be, these are absolute, the results would be 7.84 kilopascals gauge and this would be 27.44 kilopascals gauge.